Welcome to Boson Buzz, where we dive into the coolest scientific ideas and breakthroughs shaping tomorrow's world. What is the essence of you? Is it your physical body, the collection of atoms and molecules that form your flesh and bone? Or is it the unique, intricate pattern of your memories, your thoughts, your personality, and your consciousness, the invisible software running on the wetware of your brain? For as long as we have contemplated our own mortality, we have dreamed of escaping the finality of death, of preserving the self beyond the decay of the body. What if you could back up your mind, like backing up the files on a computer? What if your consciousness, your very you-ness, could live on in a digital world, a simulation, long after your biological body has ceased to function? This concept, known as whole brain emulation or mind uploading, is one of the most ambitious, profound, and controversial goals in all of science. It pushes the very boundaries of what we believe is possible, forcing us to ask not just can we, but what are we? It is a quest that stands at the intersection of neuroscience, computer science, and philosophy, challenging our most fundamental understanding of life and identity. The first, and truly monumental, challenge on the path to uploading a mind is creating a perfect map of it. Your conscious experience, your memories, your fears, your joys, is not a vague cloud of energy or a soul separate from the physical. The current scientific understanding strongly suggests it arises from an unimaginably complex physical structure, the human brain. This 3-pound organ houses a staggering 86 billion neurons, each one a sophisticated biological processor that can connect to thousands of its neighbors. These neurons communicate through a vast, intricate network of pathways called synapses, which number in the hundreds of trillions. This specific, unique pattern of connections, the complete wiring diagram of every neuron and every synapse, is known as the connectome. Think of it as the most complicated circuit board or social network in the known universe, where the precise structure and strength of each connection defines the function, storing your memories and shaping your personality. To even contemplate uploading a mind, we would first need to map this entire three-dimensional circuit with near-atomic precision, tracing every single wire and cataloging every connection's strength. We're not just taking a static picture of the brain, we're trying to create a perfect, dynamic, and exhaustively detailed map of its entire architectural and functional essence. This task is often compared to mapping every star, planet, and asteroid in a galaxy, but on a microscopic scale and with far greater complexity. How could we possibly create such an impossibly detailed map? The proposed method is as staggering in scale as the goal itself. It would likely involve a process of destructive scanning. A preserved brain would be carefully embedded in a resin, and then, sliced by vanishingly thin, microscopic slice, each one thinner than a human hair, systematically imaged using technology like powerful electron microscopes. Each slice would be scanned to reveal the neurons and, crucially, their synaptic connections. This process alone would generate an almost unimaginable amount of data, on the order of zettabytes, equal to a significant fraction of all the digital information in the world today. But a static map is not enough. The second, even more daunting step is simulation. You would need a supercomputer, or a network of them, of such immense power that it could run a real-time, functional model of this mapped brain. This digital replica would have to mimic the electrical and chemical signaling of the biological original, simulating the firing of neurons and the flow of information across the connectome. The theoretical hope is that if the simulation is perfect enough, this digital brain would wake up, think, remember, and be conscious, a digital ghost emerging from the machine. While scientists have successfully mapped the entire simple 302 neuron nervous system of a tiny worm and are making painstaking progress on the far more complex mouse brain, scaling this Herculean effort up to the human brain is a challenge of such magnitude that it may take a century or more of relentless technological advancement. However, the most profound obstacles are not merely technical. They are deeply, fundamentally philosophical, striking at the heart of what we believe consciousness to be. This is where the concept of uploading hits its most perplexing wall. Imagine this scenario. A perfect, atomically precise simulation of your brain's connectome is created and activated. Would this digital entity truly be you, or would it just be a flawless copy, a sophisticated replica that has all your memories and sincerely believes it is you? It would recall your childhood, know your secrets, and feel connected to your loved ones, but it would not have lived your life. The original, biological, you would have ceased to exist during the destructive scanning process, while this new digital twin awakens in a machine. This highlights the critical difference between a continuation of your conscious stream and the mere creation of a copy. Furthermore, our minds are not isolated computers. They are deeply and constantly intertwined with our bodies, influenced by a flood of hormones, immune responses, and rich, real-time sensory input in ways we are only beginning to understand. A brain in a computer would be utterly disembodied, lacking this essential, lifelong conversation with a physical form, raising the haunting question of whether such a pared-down, isolated existence could ever be truly whole or recognizably human. Beyond the philosophical quagmire lie practical hurdles of almost science fiction proportions. The data storage required for a single human connectome is colossal, demanding entirely new forms of computer memory. The processing power to simulate a human brain in real time does not yet exist. We would need computers millions of times more powerful than today's best supercomputers. The scanning technology itself, capable of nanometer resolution on something the size of a human brain, is still a developing field. And perhaps most dauntingly, we still lack a complete theory of how consciousness arises from neural activity. We are trying to replicate a system whose fundamental operating principles we do not yet fully comprehend. It is like trying to build a perfect replica of a modern computer chip using only 18th century technology and knowledge. We might see the structures, but we don't understand the physics that makes it work. This grand quest is as much about filling these vast gaps in our basic scientific knowledge as it is about engineering. Despite the distant and wildly speculative nature of the ultimate goal, the determined pursuit of whole brain emulation is already yielding tremendous, tangible, and immediate benefits for science and medicine today, making the journey incredibly valuable regardless of the final destination. The revolutionary tools and techniques being developed specifically to study the brain's ultrafine structure are dramatically accelerating the entire field of neuroscience. They are providing us with an unprecedented clarity to understand the physical basis of devastating neurological diseases like Alzheimer's and Parkinson's by allowing us to see precisely how synapses break down and critical neural networks fail over time. The complex computational models of smaller neural circuits, created as stepping stones to a full brain simulation, are providing vital insights into conditions like epilepsy, schizophrenia, and autism. Beyond medicine, the quest itself forces us to deepen our fundamental understanding of cognition, memory, learning, and the very nature of consciousness, thereby pushing the boundaries of computer science, physics, and philosophy. The powerful new AIs and sophisticated data analysis techniques created to handle this immense and complex biological data are finding valuable applications in countless other fields, from accelerating drug discovery and genomics to designing new materials. The journey itself, for all its daunting challenges, is proving to be as valuable as the destination, driving a wave of innovation that is directly improving human health, expanding knowledge, and reshaping technology here and now. Mind uploading remains a theoretical frontier, a grand challenge that sits on the far horizon of scientific possibility, not an imminent technology. It is a concept that forces us to confront the deepest questions about the nature of reality, identity, and what it means to be human. The ethical implications are staggering, from the moral status of a digital consciousness to the potential for creating untold suffering in a simulation. Whether or not a digital ghost ever becomes a reality, the monumental effort to understand how to create one is fundamentally transforming our relationship with the human mind. We are mapping the unknown continent of our own consciousness. With every new discovery in neuroscience and every leap in computing power, we are not just learning how to potentially preserve a mind, we are learning what it means to have one in the first place. The true legacy of this quest may not be digital immortality, but a far deeper, richer, and more humble understanding of the biological miracle that exists inside each of our heads right now. If you found this as fascinating as I did, do me a huge favor and hit that like button. Share this video with anyone who loves science or just cool futuristic tech. And of course, if you want to stay updated on this and other amazing breakthroughs, make sure you subscribe to the channel. Thanks for watching, and I'll see you in the next one.